Welcome back to AI Codecast, everyone. Ready for another deep dive?
Absolutely. Always excited to tackle some interesting algorithms.
Today we're looking at the sort colors problem.
Ah, yes, a classic.
It sounds pretty simple when you first hear it.
Deceptively simple for sure.
Yeah, you're given an array with just D zeros, ones, and twos.
Representing colors like red, white, and blue
Exactly. And the goal is to sort them in place.
without using any built-in sorting functions, of course.
Right, so we have to get a little creative with our approach.
It's all about finding those elegant solutions.
So where should we start with this? Maybe just try a simple brute force approach first?
Yeah, I think that's always a good starting point, just to get a feel for the problem.
All right, so we could just go through the array and count how many times each color appears.
Yeah, like how many vowels, how many ones, and how many twos.
And then just overwrite the original array based on
so
those
look at-
counts.
Right, where the zeros and the ones and finally the twos.
That makes sense. It's pretty easy to understand.
It's definitely a valid solution.
But I feel like it might not be the most efficient way, especially if we have a huge array.
Yeah, you're right. Going through the array multiple times can get pretty slow.
Especially for really large data sets.
We want to find something a bit more clever.
Yeah, something faster.
So how can we minimize the number of times we have to go through the array?
Ideally, we would do it all in one pass.
Now you're thinking. Imagine the array as a flag with red, white, and blue sections.
Okay, I could picture that.
How would you maintain those sections as you go through the array? Just once.
That's an interesting way to think about it.
Mm.
Maybe use some markers to keep track of where each color section begins and ends.
You're on the right track. That's the core idea behind the Dutch national flag algorithm.
The Dutch national flag algorithm. Okay, tell me more.
Well, think of it like this. We have these 3 pointers, right? We can call them low, mid, and high.
Okay, like signposts.
Marking the different sections of our flag, our array.
I'm picturing it. So what exactly do these pointers represent?
So the low pointer, that one keeps track of the end of the red section.
Okay,
Everything before it should be all those does.
gotcha. And the high pointer.
High marks the beginning of the blue section.
So everything after that is twos.
Exactly. And then we have mid,
Our middleman.
our worker bee. It starts at the beginning of the array
Okay.
and moves forward, checking each element as it goes.
Our little explorer.
Precisely. So mid's job is to figure out where each element ultimately needs to go.
Got it. So what happens when mid encounters different values?
That's where the fun begins.
Got
So
it.
let's say mid finds a 0, right?
Our red.
What do we do then?
Well, I guess we need to move it to the red section.
Exactly. We swap the element at mid with the element at the low pointer.
Okay.
So that extends our red section at the beginning.
Makes sense. Then we move both low and mid one step forward.
Right. Now, what if mid encounters a 1 or white?
Well, the white section's in the middle.
Yeah.
So if it finds a 1, it's kind of already where it needs to be.
Exactly. No need to swap. In that case, we just move mid forward.
Simple enough.
Okay.
And what about when mid comes across a 2?
Ah, our blue. This is where it gets a little interesting.
Okay.
When mid finds a 2, we swap it with the element at high.
And then move the high pointer one step back.
You got it.
But why don't we move mid forward here as well?
Good catch. We don't move mid because the element we just swapped into that position, we don't know what it is yet.
Oh, I see.
It could be a 0 or a 1 or even another 2.
Then we gotta check it again.
Exactly. So we keep doing these swaps and moving our pointer until mid crosses over the high pointer.
Ah, okay.
That means we've examined and placed every element correctly
Our flag is all sorted. Reds, whites, and blues, all where they should be.
in just one pass.
Super efficient. But are there any trade-offs with this algorithm?
You're always thinking ahead. Well, it works amazingly well when we have these 3 distinct values.
Right, colors.
But it doesn't generalize so well to more than 3. It's a specialized tool, you could say.
Specialized, but powerful. Okay, so this is one really cool way to solve it. Are there other approaches we could use? Maybe ones that can handle more than just 3 values, even if it takes a little longer.
Absolutely. Let's look at counting sort next.
Uh,
As you might guess, this one involves, well, counting.
Counting, huh? So we're tallying up how many of each value we have.
You got it. This one uses 2 passes through the array.
Okay,
The first pass is all about counting.
but we have a bucket for each color.
Exactly. And as we go through the array, we drop a token into the right bucket for each color we encounter.
I like that visual. So after the first pass, we know how many of each color we have.
What do we do in the second pass?
We use those counts to rebuild our sorted array.
Okay.
We start by placing all our zeros, our reds,
Right.
then the right number of ones, our whites,
And then the 2s or blues?
based on those counts from the first pass. It's like rebuilding our flag from the ground up, making sure each color has the right number of elements.
That's pretty straightforward. Is counting sort more efficient than the Dutch national flag algorithm? That's where it gets tricky. It depends on the range of values we're sorting. If it's small, like just our three colors, it's pretty efficient.
Okay, but what if we have a lot more values?
That's where counting sort might run into trouble. If you're sorting numbers from like 1 to 1,000,000,
Whoa,
you need a counting array with 1,000,000 slots.
that's a lot.
And that can take up a ton of memory.
Okay.
So it's not always the best choice for larger ranges.
So it's a trade-off.
Huh.
Simple and fast for small ranges, but watch out for that memory usage with larger data sets.
Exactly. Each algorithm has its own strengths and weaknesses.
We've got this super efficient Dutch national flag algorithm, and then counting sort, which is simple, but kind of limited by the number of values. Are there any other ways to approach this? Maybe something that kind of bridges the gap between these two?
You're full of great questions today. Let's talk about a variation using three pointers, like the Dutch national flag algorithm.
Okay.
But this one uses two passes through the array.
2 passes and 3 pointers.
All right.
I'm intrigued. How's this one work?
Think of it like a step-by-step approach to partitioning our array. So in the first pass, our goal is to move all the zeros, the reds, to the beginning.
Like building that red zone at the front.
Exactly. We use two pointers for this.
Okay.
One to keep track of where the next zero should go.
And the other one just moves through the array.
Right, swapping zeros into that red zone as it finds them.
So after that first pass, all our reds are lined up nice and neat. What happens next?
In the second pass, we do the same thing for the ones, the whites.
Okay.
Starting right after the red zone.
Right.
And we use two pointers again.
To move all the ones into place,
Right next to the red zone.
creating a white zone.
You got it. Now we're taking care of the zeros and the ones.
So the twos, the blues, they're just left at the end.
Automatically in their correct position, our blue zone.
I like it. Each color gets its own designated zone.
It's a bit like a domino effect.
Okay, but this one takes 2 passes, right?
Yep.
Is it as efficient as that one-pass Dutch national flag algorithm?
Not quite. That one-pass algorithm is still the fastest for this particular problem.
Yeah.
But this two-pass approach, it's a great way to really see how we partition the array more gradually.
Yeah, like it breaks down the process into smaller steps.
And it might be a bit easier to understand for some folks.
It's like learning to walk before you can run.
All right, so we got 3 different ways to tackle the sort colors problem, each with its own pros and cons. Before we wrap up, can we just do a quick recap of each approach?
Sure. So we started off with that super efficient Dutch national flag algorithm,
Right, our one-pass solution.
but it's really good for when we have just those 3 values.
Red, white, and blue.
Exactly.
Yeah.
Then we talked about counting sort,
Bucket approach.
which works great for small ranges of values.
As long as we don't run out of memory.
Right. Got to watch out for those larger data sets. And lastly, we went over that 2-pass approach with the 3 pointers.
A more step-by-step way to partition the array.
Yeah, and it might be easier to wrap your head around.
I like how we have all these different options. It's all about picking the right tool for the job, right?
Absolutely. And one thing that's cool about all these algorithms is that they do in-place sorting.
You got it.
We're not using any extra arrays or anything.
It's all happening within that original array.
Why is that so important? Especially for these coding challenges.
Well, imagine you're working with a giant data set, like millions of elements.
Ooh.
If you start creating extra data structures for sorting.
You could run out of memory.
Exactly. And that can really slow things down or even crash your program,
Makes sense. So in-place sorting helps us save memory.
especially when we're dealing with those massive amounts of data.
It's like being efficient with our resources.
Now, these algorithms are pretty neat on their own,
Yeah, they're fun to think about.
but I think it's also important to see how they connect to the bigger picture of computer science.
Like how the Dutch national flag algorithm uses partitioning.
Right, which is a key concept in lots of other sorting algorithms like Quicksort.
That's one of the more popular ones, right?
One of the most efficient, for sure. And it also uses this divide and conquer approach.
Divide and conquer, what's that?
It basically means breaking down a problem into smaller subproblems
Okay.
and solving those subproblems recursively.
Oh.
So in Quicksort, we keep partitioning the array around a pivot element.
A pivot element.
Yeah, we choose one element,
Okay.
and then we put all the smaller elements to its left.
And the bigger ones to its right?
Exactly. So you see how the Dutch national flag algorithm is like a simplified version of that.
Yeah, kind of like a specific case tailored for just those 3 values.
Precisely. And understanding how that works can really help you understand more complex algorithms like Quicksort.
It's all connected. Now what about counting sort? We said it's a non-comparison based Sorting algorithm.
Right.
What makes those different?
Well, unlike algorithms like Quicksort or bubble sort,
Which compare elements to figure out their order?
right, non-comparison based algorithms, they use information about the data itself.
Like how often each value appear?
Exactly. So instead of asking, is this element bigger than that one?
They just use the counts to put everything in the right place.
You got it. That's why counting sort works so well when we have that limited range of values. It can directly calculate the final position of each element based on its count.
That's pretty clever.
Hmm.
So we've explored these 3 different sorting algorithms today.
Just a glimpse into the world of sorting.
There are so many more out there.
And as we've seen, each one has its own strengths and weaknesses.
So it's important to understand how they work and when to use them.
Exactly. And the best way to really learn is to try them out yourself.
Yeah, experiment with different data sets and see what happens.
Have fun with it.
That's what coding's all about. And hey, if you ever get stuck, the AI Codecast community is always here to help.
We love seeing your questions and insights in the comments.
We're all on this learning journey together.
Absolutely.
Well, that's all the time we have for today. Thanks for joining us on this deep dive into the sort colors problem. Until next time, happy coding, everyone.